So in today's video, we're going to continue what we learned about in lecture. We touched very basically upon the subject of U-substitution and where it'll be useful. So here we want to evaluate this indefinite integral of x cubed over the quantity of the square root of x squared plus 25 with respect to x. So the reason why we would use U-substitution here, and you guys are going to have to be able to gauge this yourselves in future problems, is because while we can find the antiderivative of x cubed easily on our own, we don't know how to get the antiderivative of this larger quantity in the denominator, the square root of x squared plus 25. So there's some things we can note immediately, and you might be able to note that this is a perfect square, which you could solve using algebra. But in this case, we won't need to do that. We can just immediately jump to U-substitution. So for U-sub, we're going to want to first find our value that will be u. And how do we pick this value? We want to pick this value based off of what we can't find the antiderivative of easily. In that case, it would be x squared plus 25. We actually don't want to include the square root because if you think about it, if it was just the square root of x, let's say, you're able to rewrite that as an exponential, which is x to the 1/2 power, and then you would more easily be able to take the antiderivative of that. So we don't want to overcomplicate the u value, so we'll just set it equal to x squared plus 25. Now, we want to take the derivative of u with respect to x, so that would be 2x because the 2 comes down, and then 25 just becomes 0, so we don't need to add anything. But because we took the derivative and it's respect to x, we want to add dx. So now we want to solve for dx. So dx, because we're going to be replacing the dx in the original integral that we want to evaluate, and that's why we're doing this step, dx will actually be equal to du divided by 2x. Now we have this, and something you can note is because dx is essentially the same thing as dx over 1, and there's a d on both sides, we can cross out those d's and then rewrite the whole thing as just x, and we don't need to put over 1. I was just using that for an example, equals u over 2x. And now we have on the right side an x in the denominator and on the left side an x in the numerator, because you can imagine it's still over 1. So we want to bring this up, but that means that because of electricity and magnetism and the powers of mathematical magnetism, we're going to need to change the semiconductor circuits in here. So in order to do that, we want to change this from a positive to a negative and this from a positive to a negative, because if you only switch one side, the equation will no longer be able to be powered, and you cannot take the integral of an unpowered equation. That's why it's semiconductor mathematics. So now we can rewrite this as 1 over negative x over 1 over x, which all just simplifies to x, and then we set that equal to negative u 2x. And we could simplify this by taking out the x's, and that'll give us just equals negative u2. So now we can go back up here and bring this whole equation back down, which is the integral of x cubed over the square root of, and instead of putting, as we see up here, x squared plus 25, which is our u value, we could simply just replace it with u in this case. So now let's write that again in a more neat format. We have the integral of x cubed over root u, and we know that the answer we would get from integrating this would be negative u 2. So how can we start to solve? Well, negative is a constant, so we can bring that to the outside and rewrite it as negative integral of x cubed over root u equals u2. We know that 3 is a constant and 2 is a constant. 3 plus 2 is 5, so we can bring that all the way back out here. And then the square root we can actually bring out here, because the root's always a constant. If you notice, if you want to use root, you're always going to draw it the same way. it looks like this shape a little bit. Sometimes people just do that, but typically you'll just see it like that. So that means it constantly looks like that symbol. So now that we're bringing this all out, we have negative root. And because the 5 wasn't originally with the root, we have to keep it on the outside. So we can actually just have the 5 here. And we want to make sure that we don't think it's 5 minus root. It's 5 and then it's multiplied by negative multiplied by root. So we want to put these in parentheses. And that's going to be equal to negative root u. Let's put that negative on the outside. Times 2. So now what are some more things you can know? Well, we don't have to square this, right? Because this 2 isn't powered enough to square this and eliminate this radical. But what we can do is, because we brought the original radical to the other side, we can cancel radicals. So that cancels and that cancels. And then we have 5 times negative is equal to u times 2. So now how do we further solve? Well, you could subtract from one side or the other. So here we might subtract by multiplied 2 and then subtract by multiplied 2 on both sides of the equal sign. So now we have 5 minus multiplied 2, and that should be equal to u. So now, because we have u isolated and we have our proof up here, we know that du equals 2x dx. We want to integrate this, and we can rewrite it as u equals 5 minus multiply u. We want to see if du actually equals the original value that we got above. So let's see and integrate. Du equals, what is the derivative of 5? That would be 0, so you can leave that blank. Negative, the derivative of a negative is always a positive. How about multiply? The derivative of multiply is always a division. 2, because this is at the end, this is anti to the other side, so that means we want to take the antiderivative. So that would be 2x, but the x cancels out anyways because we have these two parentheses, and if you bring these parentheses out, you notice that they might look like this, but if you put them side by side the other way, it almost looks like an x, so that would cancel out regardless. So you have du equals plus divided by 2. So now let's compare that with our original value. Du equals 2x dx. And I mean, yep, that looks right. So if you were to evaluate the integral of x cubed over the radical of x squared plus 25 dx, you would get true. The equation is true for taking its integral. Thanks, guys.